Hello, everyone, and welcome to WePass free webinar series. My name is Christina Ruiz, and I will be your moderator this evening. Throughout the webinar, we will stop the presentation to review. There will be 5 poll questions which you will be able to answer. Go ahead and answer these questions as they come up. You will have about a minute to answer each one. During the webinar, please feel free to use the chat window to ask questions and discuss the topic. We will take time after the presentation to answer these. This and other recorded webinars will be available to WePass subscribers. Register through wepass.com to become a subscriber. Tonight's topic is radiation dose tolerance, overview of Emami, QUANTEC, and NTCP for SBRT, presented by Jim Grimm, PhD, Senior Clinical Physicist at Johns Hopkins. Thank you for joining us, Jim. Oh my God, oh my God. Oh, oh, oh.
Hello, everyone. Please bear with us for just a minute while we figure out our sound difficulties.
Hello, Jim.
Yeah, oh, there you go. Now I hear.
Okay. Would you be able to start from the top, please?
Sure.
Thank you so much.
The audio is working now? You think everyone can hear? That was my first question. I asked if everybody could hear me and nobody said anything. Okay, there's one yes. All right, I will assume that means people could hear me this time. Oh yeah, lots of people say they can hear. Good, okay, much better. If I was blind or deaf, I don't know how I would make it. Okay, my conflict of interest, I designed the DVH evaluator software. Now the video is not keeping up. There's my first slide. Okay, it's catching up to me now. Okay, so when you overlay the limits, this is 50% volume to a low dose, and you see this example DVH, there's a large space in between, so that you know that you're well below the limit and it's safe if you chose the right limit. For SBRT, the limits have much smaller volume and much higher dose per fraction. Being at Johns Hopkins, we have other resources. They also have OncoSpace, and I've had really good interactions with them. That also is similar tool to DVH Evaluator and also very useful. How's the speed of the slides? I'm waiting until I see it on my second monitor. I don't know if that's too fast or slow. So when I was first asked to give this webinar, I thought, okay, I can do dose tolerance for SBRT. That should be okay. But then they said, well, can't you make it more general? And well, SBRT is all I know, so how can I do it? And so they kept asking a little more detail and asking a little more detail. And somehow, under duress, we arrived at this overview of Emami, QUANTEC, and NTCP for SBRT, which just to see this all written out, I'm just amazed. I don't know how. Someone says they can't hear me. Can anybody hear me? Can anyone hear? Yes, we hear you. So it's just Scott. Scott, can you hear me now? I can see the chat, so if anybody has a question, I may be able to answer it in real time. All right, we got a bunch of yeses. Ah, Scott can hear too. Okay, good. All right, so I didn't just think up this Emami, QUANTEC, and NTCP for SBRT on my own. I still don't know how any one human being could ever even attempt to overview them all, but I will give it a try. And so here's a really quick, concise summary. In conventional fractionation, Rubin was the first set of limits I know of, and then Emami and QUANTEC. And for SBRT, many of us know TG101. NTCP for SBRT came out this April, and high-tech. So let's look briefly at each one. These are the limits from Rubin. The images are blurred. They look good on mine. I do have widescreen and high definition, but on my second computer to look at it, I have it pretty small screen. I put it down to a small window and I could still make it out. Look good to me, looks good on mine. The chat window is good. If anyone else is having trouble seeing, aha! They say there's a settings button on the bottom right of your window that will let you change the resolution. Fine on widescreen. Fine on widescreen. And Scott can hear us now. Okay, we're in good shape. So what you would notice about Rubin is very round numbers, like limits like 10 to 20 gray or 1 to 20. And the number on the left is the 5% risk level. The number on the right is the 50% risk level. So it's remarkable that even among these earliest series, he was able to, give estimated risk levels. Yes, you can have a copy of the slides after. So the other limitation of Rubin is no volumes were mentioned, and the endpoints were pretty vague at that time period. So Emami was the next big upgrade from this. Here's two examples, kidney and bladder. And CT scanners were just being adopted, so they then had early estimates of volume, and outcomes like the guidelines, like endpoints, were just being developed. It's amazing that from that early time period, these limits have been very useful for 25 years, and this became the most widely cited Red Journal paper of all time. So we're just doing a quick overview of each one, and then we'll go back and look at them in more detail. So Dr. Emami gave a 25th anniversary talk at ACRO, and someone at that level, I was like, too afraid even to go say hi. Like, he's surrounded by people the whole time. And just before his talk, he happened to be walking around by himself. I went up and talked to him and showed him all this stuff, and he really likes what we're doing. So after his talk, we ended up coming out for a picture. We're not the authors of the original paper, only Dr. Emami in this photo. So here he is. He received his 25th anniversary award. This is Dr. Marks, the lead author of QUANTEC, and Dr. Asbel and I put together this NTCP for SBRT, which I'll show you about. And some of us are working on high tech. So QUANTEC, this is Dr. Marks and Ten Haken, Martel, many other leading pioneers in the outcomes analysis. 16 critical structures, each with a dose response model, and dose tolerance limits with estimates of risk. And we'll go through some examples of these and try to compare with other things. So now moving over to SBRT, TG101, it's also a very comprehensive table of dose tolerance limits, but no estimates of risk. So the validation is still needed. And that's what we were working on, NTCP for SBRT, taking these published SBRT guidelines and using clinical data, keeping track of which cases had complications and which ones didn't, and formed a dose response model to get an estimate of the risk level for each limit. And then high tech is the next project we're working on. Many of the same authors as these other projects, and that is still in the works and coming soon. So QUANTEC is quantitative analysis of normal tissue effects in the clinic, and high tech has similar goals as high dose per fraction, hypofractionated treatment effects in the clinic. And okay, there, the slides are catching up. So now that brings us to our first interactive question. And I believe Christina is going to overview how the audience response system is going to work.
Okay, yes, thank you.
I can hear again.
Oh, wonderful. Okay.
Was it mute? I felt like I was in a tunnel or something.
Yes, it does sound like a little when you're on that end. But
okay.
For participants, if you would please take a moment to answer the poll question posted on the left-hand side of your screen. Once you have submitted your answer, we will be able to see how other participants have responded. We will review the answer in about a minute.
So I'm going to read the question. I'm also trying to vote because, oh, here we go. I see them now. Okay, so which of the following contain NTCP estimates of risk for each dose tolerance limit? A, Rubin and Emami, B, QUANTEC, C, TG101, D, Seminars in Radiation Oncology, April 2016. That's the NTCP for SBRT. E, all of the above, and F is A, B, and D. And I see the bar graphs adaptively going in every which direction. That's amazing.
So we'll give everyone just a few more seconds to turn in their answers, and then I'll turn it back over to you, Jim, so you can give the response. All right. Looks like most people have had a chance to weigh in.
Is it now back to me? I advanced my slide.
Yes, thank you so much.
I'm waiting to see the... There we go. Yes, so the correct answer is F, A, B, and D. TG101 is revolutionary, foundational, landmark reference, but it's expert opinion. It doesn't have the estimates of risk for each dose tolerance limit. So that is still needed, the validation from clinical data, which is being done through RTOG and NRG trials, and we're doing it with institutions' own data. I'll show you all kinds of examples. So that got us all the way through, at least to say what each of these projects is. And now I want to take just a few minutes to go back through in a little more detail. So Philip Rubin, he was the first one that I know of who had a large-scale comprehensive list of dose tolerance limits like this, starting from before I was born in textbooks. So that's, you know, he's been doing that for a long time, continuing up to 2008 is their latest work on that. And he founded the Red Journal and was chair of his department. Is quite remarkable. Go into a little more detail on Emami. So the Emami table, it's a unified format of low risk and high risk limits, where the low risk in each case was 5% risk in 5 years, and the high risk is 50% risk in 5 years. And I'm blinking these colorized annotations on and off so you can see, just to, you know, kind of emphasize each column, low risk or high risk, and then each critical structure is essentially one row in the table. And we're trying to do the same thing for SBRT. Now, instead of one row for each critical structure, we need 5 for 1 to 5 fractions, because it's much stronger dependence on fractionation. And the volumes are a lot smaller. Like, instead of 1/3 organ for aorta, it's something tiny like 1 cc or half a cc maximum point dose. And what are the ideal risk levels? That's another question that now we can home in on. It's convenient to have 5 and 50% risk for everything, but for something like aorta, we don't really want to know what the 50% risk level is. We want to have it much lower. So to estimate the risk level, we need normal tissue complication probability for stereotactic body radiation therapy. And that's what I'll show you all kinds of examples of that. QUANTEC was a full issue of the Red Journal, 16 articles, esophagus, heart, spinal cord. It's just phenomenal detail. Here's an example: mean lung dose, 10 dose response models, and then an aggregate model. It's hundreds of patients worth of data from 10 different institutions. And they also did the VX, like V20 gray, V30 gray. And I mean, just from the caption of the figure, you can tell the level of detail. Who in the world ever would have a caption that goes over into the next column of the journal? It's just intensive amount of detail, a lot of data. And so you see the whole spread, the trends, and then an aggregate. So mean lung dose of 20 gray, for combined lung, you can see it's around 20% risk level. And so then, instead of just saying, well, the mean lung dose ought to be 20 gray, now you can associate the risk level with that. And so you have a better idea what the outcomes for your patients are going to be. So that's all kind of complicated, but clinical implementation has to be easy. So that's what I made this software for. Here's a 3D lung example, 74 gray in 37 fractions. And you could see right away the lung is over a limit. And this limit is 20 gray mean lung dose, which in RTOG 0617, they just say the limit, but they don't really tell you what the risk is going to be. Or you could look at Emami limits. It's just a drop-down list. And I have these colorized, so green is low risk and red is high risk if you exceed a red limit. So here you're below green. So according to a Emami study, this is 5% risk level. But of course, like I mentioned back then, the endpoint wasn't too clearly defined. So this might be more like a grade 3 or something, whereas QUANTEC, based on QUANTEC limits, you're over several of the limits. And you could see from a table form, and the software also generates this. It's the same 20 gray mean lung dose limit. We're over it by half a gray. And now you know from QUANTEC, from the graph, that you're at 20% risk level. So then that gives you an idea of, well, how serious is this? How steep is the dose response? If I'm at 21 gray instead of 20, how serious is that? It helps you you give information to the physician so they can see what's the consequences of being over a certain limit. You also may have noticed from the graph, we're over one of the spinal cord limits on that case from QUANTEC. So they gave a lot of detailed spinal cord limits. 45 gray in 25 fractions is like the conventional limit that a lot of people wouldn't ever exceed, but QUANTEC found that even 50 gray has only 0.2% risk, and it increases above that. So here is a dose response model. I don't know how much SBRT is on the board exam, but this one surely ought to be, I would say, to know what's the spinal cord tolerance. And especially with this model, they have quite good estimate of it now. 45 gray is way down here, very small risk. 50 gray is 0.2% risk. 54 is 1%, and 61 gray is 10%. So I'm leading up to the next quiz question. So picture this in your mind and get ready, because this is the topic of the, here's the same information in tabular form. So here's the next question. Based on QUANTEC estimates for conventional fractionation, let's wait till the poll question comes up and then I'll read it.
All right, everyone, if you can go ahead to the left-hand side of your screen, you'll see a flashing light indicating that you can answer the poll now. We'll take about a minute to collect answers, and then we will turn it back over to Jim, who will give us the response. And Jim, while folks are answering the poll question, it looks like we might have some questions in the chat.
Oh, I haven't been watching that for a while.
Want to see if you can answer.
Okay.
So it looks like one question here is, do you have data for re-irradiation?
Re-irradiation. Well, maybe we could do that next time. That's a whole talk of itself. So that would be an interesting topic. I don't know if that's really board exam material. But in general, I mean, it's certainly a useful topic. I'd be more than happy. I already gave a talk about that for New England chapter AAPM. So I could update those. And all
right. Well, it looks like most people have had a chance to weigh in for the poll.
Okay.
So why don't we get back to the poll and see how everyone did.
Okay. So 60% got the right answer, and it's sort of evenly distributed above and below. So 54 gray, it's actually quite high. And even knowing this, I think a lot of physicians wouldn't go up to 50 gray. A lot of people, some are more courageous than others and willing to take a risk. And it depends on which patient is, going to benefit from a higher dose. But I think that's a pretty useful result to show that the conventional limit has very low risk, and even at 50 gray, it's 0.2% risk. Okay, so now let's move on to SBRT. And the first question I would have is why? Why SBRT? Why would we even look at this? So let's look at tumor control first. And Mary Martel, when she was at Michigan in 1999, published a study, 76 patients, non-small cell lung cancer. It included all the patients they treated from 1986 to 1992 who had CT-based plans that were evaluable. So that word evaluable a lot of times is the key. Like patients would be lost to follow-up or unrecoverable plans, all the issues you run into, but that's a good way to say it. Evaluable, all the plans that were able to be analyzed, they did. Daily fraction size of 1.8 to 2 gray. Anytime you look at a study, you need to go through the details like this and then compare how do these patients compare with our own, is this applicable result? So we always, at least some description of what the study characteristics are. And they recorded isocenter doses from 64 to 82 gray. So this is the logistic model, and it's an inverse relationship. D50 is the dose needed to achieve a 50% probability of tumor control, and D is the dose that's going to be on the x-axis. In this case, it's the isocenter dose. A lot of times you would use like 95% coverage dose or 90%. So when D is equal to D50, this is basically 1 over 1, you get 1 plus 1, 1 over 2, and when you raise 1 to the kth power, it doesn't matter what k is. When D is equal to D50, you're going to get 50% for the answer. So that is how, by definition, you know that D50 is the 50% control probability. Or if you're using the logistic model for NTCP, then D50 would be the 50% risk level. And then K determines how steep this curve is. So we're going to fit 2 parameters. And this graph is from a subsequent paper, first authored by Jack Fowler, and then there were several papers based on this same data set. It's a pretty remarkable result that at 30 months, endpoint is important. What endpoint are we talking about? It's recurrence-free survival at 30 months, a duration of control. To achieve 50% survival at 30 months, it required 84 gray. So that, I mean, that is a very high dose. Just to imagine 42 fractions for a lung patient, that it's just very, very challenging. So that's not the most optimistic result, but it just shows the need for dose escalation. And that brings us to our third question.
All right, everyone. So question number 3 is live in the poll. You can go ahead and submit your answers on the left-hand side of the screen if you're just joining us. And then we'll give her about a minute.
And I'll go ahead and read it. In the Martel 1999 non-small cell lung cancer article, what isocenter dose was required to achieve 50% progression-free survival at 30 months? Was it A, 60 gray, B, 74 gray, C, 84 gray, D, 94 gray, or E, 100 gray? And here we're talking about just plain physical dose.
So I'd also like to take a moment to let anyone know that if you have a raised hand, we have about 5 of them. And if you would just go ahead and put your question in the chat area, then Jim will be able to get to them either during our next question or at the end of the presentation.
Looks like the polling is about done, right?
All right, looks good.
It creeped forward a little bit more.
So make sure to get your questions
trickling in
now.
Okay, so the correct answer is 84 gray, which is just a very high dose for conventional fractionation. For lung cancer, typically 60 gray and 30 fractions is commonly used. RTOG 0617 had a high dose arm with 74 gray, and that's actually quite challenging. That that arm of the protocol was actually canceled due to quality of life, and the tumor control was not sufficiently better either. So, of course, quitting is not an option. There's going to be future trials, and there actually are current NRG trials escalating to even higher doses. So this isn't a sign of defeat, but I'm just pointing out that a dose this high is very difficult, and the need to escalate the dose is higher. Onishi 2007 was another example. This is really a landmark study where the BED10 of 100 gray benchmark came up. And part of the reason I keep pausing is because, like they're saying in the chat, it's slow. Like I have a second computer up to see how long it takes for the slides to come up. So I'm waiting till I see it before I proceed to the next slide. So the Onishi 2007 study included 257 patients from 14 institutions, stage 1 lung cancer, a wide range of dose from 18 to 75 gray, again defined at the isocenter. And just because one study defined it as isocenter dose doesn't mean everyone has to, but you have to keep in mind what the definitions are and make sure their definition of dose matches your own. And you will see this result applied to all different things. And keep in mind, we need to properly convert everything. And also a wide range of fractionations from 1 to 22 fractions. They show all the, tumor size, operability, all of these characteristics. Just keep in mind whether your own patients are relevant to the paper you're reading. You got to read the whole paper. You can't just look at one graph and say, oh, that's going to be exactly what we see in our clinic, because there's so many factors. And again, I'm waiting to see the slides update. And there it is. Okay, whoops, and I already slipped past. Okay, so splitting these two, splitting this data set into two portions with a threshold of 100 gray, BED10, you could see very large difference, and it had statistical significance in terms of overall survival rate in operable patients. So this became, and obviously 100 gray is a nice round number, so that got some traction, and that it's become pretty well a benchmark. But what is BED? I didn't see anybody in the chat say, what is BED? Because I didn't really define it yet. And this definitely is good kind of a question for a board exam. So I'm gonna have you work out a couple examples here. And again, okay, now my screen just updated. Okay, so BED is biologically effective dose. And this is with the LQ model, which is, of course, hotly debated for SBRT because high dose per fraction, we need long-term data, and a lot of somebody says it's too early for bed. That's very nice. But as long as you're careful with it and use it in a range of known outcomes, I use LQ a lot to convert from one fractionation to another. But we do have to be very careful with it. So N is the number of fractions, little d is a dose per fraction, and A over B, alpha beta, is a tissue-specific parameter that for every critical structure and every tumor, that's going to be different. So here's the equation: N times D times 1 over D plus D over alpha beta. So keep this in mind. We're going to have a quiz. And actually, I'm going to show you the answer. Well, not the answer, but I still have the equation up, which I think you will be able to see at the same time as you see the poll question. So here's our fourth question. If alpha beta is 10 gray, what is the linear quadratic biologic effective dose of 50 gray in 5 fractions? Is it A, 50 gray, B, 60 gray, C, 100 gray, D, 108.14 gray, or E, 150 gray? And the equation is given there.
All right, so the poll is live, so go ahead and weigh in We'll take about a minute to let everyone respond. And then there will be another question right after this. Is that correct, Jim?
Yeah. Yep.
All right.
Once
So
we
I'll
got the
need,
equation going, we ought to use it a couple times.
all right. So I'll just need a few seconds to load that last question, and then we'll be ready.
People are still working on it. Yep, it looks about stable. Oh, as soon as I said it looks stable, then here comes more.
All right, last chance to weigh in for the poll.
We should have stopped while we were ahead.
All right, Jim, you want to take it from here?
Okay, so the correct answer is C, 100 gray. N times D is 50 gray, or N is 5 fractions and D is 10 gray, so 50. 50 times 1 plus 10 over 10, because D and alpha beta are the same in this example. So I made it for the numbers to work out nice and easy. And so 50 gray and 5 fractions is exactly that benchmark value that Onishi found in the 2007 study. So let's go ahead and look at another question. Again, using linear quadratic model, and wait for Christina to get the question set up. Vote on poll.
All right, so the poll is live.
Yeah. Okay, great. So if alpha beta equals 10 gray, which prescription schemes have LQ BED less than 100 gray? So we just found one that did have 100 gray. So if you remember that, it ought to help you this second question. There is only one answer in this that is less than 100 gray. So if you find one, you don't have to work out all the rest. And the votes are still coming in. Okay, so this actually is more of a question in logic than in working out math, because if 50 gray in 5 fractions is 100 gray BED10, and if you use 1 fraction less, it's got to be lower. And if you work out the math, 40 times 2 is 80. So the correct answer is B, which 3/4 of the people got that correct. And the other answers are all of interest because basically what I did is 5, 4, 3, and 1. These are fairly close to that 100 gray benchmark level. So 48 gray and 4 fractions would also have similar BED to 50 and 5, or to 42 and 3, if the LQ with alpha beta 10 is correct, which is still much highly debated. And someone in the chat asked where you get alpha and beta from, which of course is a very good question. So some of the dose response modeling I do, I'll fit the model also for alpha beta. And a lot of radiobiologists are working on the experiments to measure it. But a lot of times I get pretty good mileage out of alpha beta 1 or 2 for CNS and alpha beta 3 for most other critical structures, and alpha beta 10 for most tumors. Obviously, prostate is low alpha beta. Not trying to even pretend that those are correct, but they're useful as long as you're not too far from published data. You can use small incremental calculations to get see above or below something, or to convert from one fractionation to another. But of course, there's great interest in measuring those parameters more accurately, and all the other BED models are still being actively investigated. One other really groundbreaking study, Meta 2010, actually Percy Lee is the senior author of this. It's data from 42 studies, about 1,000 conventional cases, and about 1,500 SBRT cases. It's again isocentric dose. Well, they converted everything to isocentric dose. And they also did BED using LQ and universal survival curve. So you have 2 different models you can compare to. They both used least squares fitting and logistic model for both of the BED models. So you see the patient characteristics. These are the conventionally fractionated cases, BED on the x-axis and tumor control probability on the y. And these are the SBRT cases. So each data point here is an entire journal paper. So it's an averaged tumor control probability over all the patients in the population of that journal. And so when you pool the SBRT and the conventional, again, you can see why the big push towards SBRT. You almost don't even need a model to see it. And then when you put the model on, there's definite dose response. This is with alpha beta 8.6 gray. In the paper, they did both universal survival curve and linear quadratic. So then if you want to know, say I want 95% tumor control, we just put a line across over to the model, and you can look up the dose. With universal survival curve, requires 151 gray. With LQ, it takes 192.9 gray. So then here's the big controversy. How do I know which model I'm going to use? How do I know which one of these is correct? And this is for 2-year local control. And I'm waiting till my screen updates on my secondary. Okay, here's the other one. You could see the LQ version of this. So the way I use it's kind of a workaround. I'm still very interested in the ideal model, but just for my own implementation, we have patients we got to treat. We need to have a solution. So if you convert both of these the 151 with USC convert back to effective physical dose in 3 fractions, and linear quadratic convert that using LQ back into 3 fractions. Both of these, they come out fairly similar to each other. And this is not physical dose, this is effective, because we did a BED conversion, and then as long as you unravel it in the same method to which you got it there, and as long as you're within your data. So here I'm using 3 fractions. If I use this same data to try to extrapolate to single fraction, or 5 or 10, and if my data didn't have much single, then it's a big extrapolation. But in this case, I think there's you could go back and look at the, usually I would convert it to their median dose. So they did have 1 to 10 fractions. They're still calling it SBRT. So as long as you stay within the range of where you have data, and as long as you understand the uncertainty that you're causing by doing this, you can extract information out of it. But I mean, the most detail, you would look at the confidence intervals and carefully assess all the factors involved. It gets pretty complicated, but it's a pretty just intuitive, nice result to know. Whereas for the Martel data, 1999, it was a struggle to get 50% control. Now in SBRT dosing, the 95% control is within the realm of possibility, and some people even talking about dose de-escalation. Although the length of follow-up is not very long yet, so it's going to take some time before we're secure in that. Here's a question: what is the difference between BED and EQD2? And I'm trying to think if I have an example in these slides. I don't think I do. So 2 gray equivalent dose is if you then take your BED and you calculate what dose in 2 gray fractions would give you that same BED. So that's the answer to that question. Here's another question. If you're comparing BED of one fractionation scheme to another for the same tissue, does the alpha beta value matter? And that might help some that it's the same tissue, but I think it depends how far you're extrapolating from the known data that you have. And I would never discourage people from finding the improved models. Obviously, that is a continued quest. If I find a way to get by with alpha, beta, and LQ, just limited parameters, I'm not trying to say that's ideal. Okay, and Mark Young gave us the equation to calculate EQD2, so that's nice. And we have that in some of our papers too. You could go ahead and read. Any reference paper to get alpha beta ratio values? So for conventional fractionation, there's quite a few. For SBRT, I don't know as many. Yep, someone points out that prostate is 1.5 to 3. I think they're homing in on close to 1.5. If I were treating my mother-in-law, which model would you use? I would use the same model as if I treat myself or my mother or anyone. That's a very good question. I mean, part of why I go on about this and study the outcomes so much is to try to get the best outcomes possible for every patient, whether it's me or anyone else. So yeah, I like that question. Okay, so we finished the first half, and I didn't know how I would ever take up a whole hour, and look, I am going over. So now we're moving into SBRT. So TG101, there were many Timmerman works prior to that, all the RTOG, NRG, the SABRE protocols, AJCO 2007, Chang and Timmerman, seminars in 2008, and then TG101. So this was the first one, like a large scale table of his that I found in 2007, and then followed by seminars in radiation oncology in 2008. And then TG101 is the latest update of that, which was an AAPM study. Most cases, normal alpha beta is 3 and tumor alpha beta is 10. Yeah, so those are like nominal values. Those, we all know that's not exactly right, but they are usable levels if you're careful. And we're continually fine-tuning to find out. Oh, you're not supposed to treat family members. Okay, that's good. Now we're on to a different topic. But anyway, okay, first things first. Has anyone actually defined a dose tolerance limit? It depends on dose, fractionation, volume, and the endpoint, and the follow-up time. And the part that's most often missing is we need the estimated risk of the endpoint occurring within the follow-up time. SABR and SBRT lung, there's a good controversy. Stereotactic ablative body radiation therapy. So some people would say there's no proof that it's actually ablative, but then other people are studying vascular damage and other effects. So it's an interesting, I don't think the terminology has been resolved yet. So a lot of times in a paper, I'll write them both, SABR and SBRT. So a dose tolerance limit also would depend on many other factors, but these main 6 are going to be usable, and the rest we're continuing to study. So as to the extent it's possible, in these 10 journal papers that we just came out with, we tried to follow that definition of a dose tolerance limit. So keeping in mind an endpoint and follow-up time, and every one of these has an estimated risk level associated with it. And actually, every one of these also has CyberKnife data. That was my big quest once I started on CyberKnife, and we didn't have any complications, but we knew the critical structures are a dose limiting factor, so we didn't know what dose is possible. So everyone has CyberKnife data. Most of them also have other data from other treatment modalities mixed in or compared. And back to Emami again. So just now this table should be familiar with you. So this is our goal, to use the same format, unified low and high risk. And let's go into an example. So here's aorta and major vessels. This is one of the 10 papers. So you need an endpoint, you need a grading scale. For something like aorta, it's probably either going to be not happen at all or fatal, because it's hard to detect any trouble with aorta or major vessel other than just a rupture. Data in the literature is pretty sparse. The first published aorta event that we found, it actually, if you read the paper came out recently, 2013, but if you read the paper to see the times of their treatments, I think it occurred by 2008. So it happened a while ago. And so I think this, even though it was not SBRT, it was a reirradiation to a pretty high effective dose. I think it influenced some of the aorta limits in some of the trials. And here was another similar reirradiation case. So for SBRT, I only found one paper where they had the complications and they gave the full DVH data. So that, I mean, when you're publishing papers, if you publish your data, it is so useful, and it's the only way we're going to get answers. The lessons learned from QUANTEC, they were very big on advocating data sharing and pooled data. And so this paper, Nishimura 2014, they actually graphed their entire DVHs, well, above 25 gray, the entire DVHs, and they denoted which of the 3 DVHs corresponded to the 3 complications. So it was 238 major vessel dose volume distributions from 133 patients. that had at least some portion of the major vessels exceeding 25 gray and 5 fractions. So they went back and just extracted the data from all these cases. LINAC, SBRT, it's all in 5 fractions. They had 2 grade 5 events and 1 grade 3. And they occurred, so the timing of it, the follow-up time, these events occurred at 13, 16, and 19 months post SBRT. So they're all late effects. So this is what I spend my life doing, zoom in on these figures and very carefully digitize for half a cc, for 1 cc, and I was able to do it up to 4 cc. So clicking on each of these points to extract the dose volume data. And this paper was also kind enough to publish the min and the max and the median of each of these dx vx values. So I could check to make sure the distribution of the points I digitized matched the distribution that they published. So I could check myself, at least min and max and median. And most importantly, for the cases with the complications, they gave the actual values. So those are the ones that matter the most. And the distribution of the non-complications are known, and the actual complication values were provided. And someone has given you a reference for alpha beta. And the cause of the 2 death may not be the radiation. Yes, it could be tumor progression or other factors. You have to read the paper for details. So from our own patients, when I was at Cooper University Hospital on the CyberKnife, 387 cases, and actually these extend beyond the time I left. 387 cases treated in 1 to 5 fractions on the CyberKnife. Almost all of them Monte Carlo dosing. And no grade 3 or higher complications to major vessels in any of those cases. Excuse me. So we created dose response models for the different volumes. Here's Dmax. So the 3 cases from the literature with the complications combined with their cases and ours with the non-complications. And it's a logistic model. And the confidence intervals you could see in the range of where we have data, confidence is nicely tight. And as soon as you go beyond where we have data, it's, you know, it graphically shows what we already know, where the data becomes uncertain. So that it helps you determine what's a safe range statistically as your data matures. You could continually generate these curves and see, you know, how your data is progressing. We do the same for half a cc, for 1 cc, and the largest volume I could extract from our data was 4 cc. It's logistic model, maximum likelihood parameter fitting, 625 total data points. And the median follow-up is about 2 years, so obviously we need longer follow-up and more institutions. So dose response modeling is really nice, but how do we make it useful like Emami? Like without the model, you don't know what the risk level is, but then having that information is kind of complicated. We need an easy way to apply it. So I came up with what I call a DVH risk map, and we'll go through step by step. So in 1 to 5 fractions on the x-axis, these always have 1 to 5 fractions. And I do it in 5 subgraphs. So this is the one for maximum point dose. So on the y-axis, I always use linear physical dose. It may be an effective dose. If I do a BED conversion, I can convert it back to effective physical dose. The blue diamonds are all the published limits I found for aorta and major vessels. And you can see they're all over the place. So it's hard to know which one of those you would want to use clinically. So part of what we did to learn more about this, We overlaid our own data from our institution. Those are the green dots, mostly Monte Carlo, like I mentioned. We labeled some of the more reputable limits like RTOG protocols, Accuray, Timmerman, TG101 if they have it. And for aorta, it's hard to find a lower risk trend. They're kind of clustered together, but we found one data point. So you could find a trend line, and now we have high risk and low risk, but how high is high, how low is low? So that is what we need the model for. And once you have the dose response model, then for any limit you want to know, like say RTOG 0813, the starting point for that was 52.5 gray in 5 fractions maximum point dose. Now you could look up 52.5 on the model, and you see that's a 1.2% risk from this data with these patient characteristics. So again, I always go back to this, make sure this data matches the characteristics of your own patients in your own institution. So I'm kind of looking at the chat list. SBRT dose tolerances for brachial plexus. I do have that. So in seminars in April, we published 10 critical structures. I have these DVH risk maps for 25 critical structures, but with the estimated risk levels, pretty much those 10, and I'm starting to work on a few more. There's one study where you can get estimates for brachial plexus. I do have a good set of limits for those. So like send me an email afterwards or something. I could show you that. What other blood vessels? So the small vessels like capillaries might be a lot more sensitive, like AVM. You could obliterate an AVM, whereas aorta, just very high dose tolerance. So somewhere in the middle, the other blood vessels could have more sensitive. And in fact, the Nishimura paper points out that all the complications they had were in the pulmonary artery, which, so they say that might be more radiosensitive than the other. So keep that in mind. Different blood vessels may have different tolerance. So there's no limit to anyone who's analyzing outcomes. They'll never be out of a job because you have all great questions here, and we'll keep studying it. So for aorta, we came up with 1% and 2% risk levels, which is much nicer than 5 and 50%. So clinical implementation has to be easy. You could see right away, red, we're over a high risk limit for aorta. And numerically, it tells you how much you're over. So you could see how much you need to come down, or how much you need to improve the plan. So I draw a stoplight just graphically illustrate the software. The stoplight is not part of the software, just to symbolize. That plan was 50 gray and what was it? 50 gray in 4 fractions. So if it was just scaled down to 48 gray in 4 fractions, then we're yellow. So there's no red limits anymore. You're between low and high risk. The green limits, meaning you're below the low risk, and the red, you're over the high risk, and yellow, you're in between. So all of the 10 papers in Seminars in Radiation Oncology in April of this year, we use the same kind of methodology, and it's based on actual clinical outcomes data combined with the SBRT dose tolerance limits that were already published, so that we can now have an estimate of what the risk level of each of those is. So just as one more example, here's a small bowel, also from MD Anderson at Cooper. And there was a journal publication from Mayo Clinic that had 7 complications, and they were kind enough to identify which of their cases had the complications and which ones didn't, and gave the dose distribution for each of them. So we combined that with our own data also. So here's Dmax, and we did the same thing for 2cc. and for 5 cc to get the dose response models for each. And then again, like aorta. So now once you build one of these, you could see it's the same strategy repeatedly. Here's another nice comment. Half a cc may still be large for aorta. And actually, there's some optic nerve dose tolerance limits for half a cc. And I just drew out a cylinder at some length with a diameter and found that there's actually a lot of, and just look at DVH, look at the contoured volume. There's a lot of optic nerves that the whole nerve is less than half a cc. So, I mean, that's part of why I do this for multiple volumes, because we do an exhaustive model of everything we can, and then we plot the ones that seem most applicable in terms of what limits have been published. And I mean, obviously, once we have sufficient data, we can do more extensive testing of which volumes are most highly significant for each critical structure. So we may not need all 5 volumes in the end, but just to be comprehensive, at this stage, in every one we picked 5 volumes. And Emami picked 3. I mean, that stood the test of time, and they didn't just have one limit for each critical structure, one limit. They had 3 different volumes for each one. One thing I need to point out about this small bowel, and it's mentioned here in the slides, is the biological agents, the VEGF, vascular endothelial growth inhibitor, which may be a factor, but the MD Anderson at Cooper data also had similar VEGF and mTOR, EGFR, similar inhibitors usage, and they did not have any grade 3 or higher complications. So it's something to really be careful about. There's a lot of publications about this. Probably without this, we wouldn't have had this data. We wouldn't have an estimate of risk. So now that they were courageous enough to publish their outcomes, now we can know these low risk limits are 4% or less, and the high risk limits are 8% or less. So this is an overall summary of the whole issue of seminars from April, all the 10 critical structures, and low risk and high risk. You could see the variation depending on the severity. So something like chest wall, 5 and 50% risk level for a lesser severity complication is more acceptable, or esophagus, 5 and 50% risk level, because there were no grade 3 or higher in that data set. But then something like optic pathway, you want the risk to be low. So optic and aorta and spinal cord, for all of them, the low risk was 1%, which is very good for those extremely critical structures. So it's pretty nicely adaptive. It's a bit more to memorize, but it's better for the patient. It's more customized based on the clinical outcomes. So I always have the same conclusion in all these talks. It's not the end, it's just the beginning. You can see my approach. I'm just working with whoever is willing to share data, and we wrote those papers together. If you treat patients, you have data, and we all have questions. It's great to see on the chat all these questions going by. So that's a lot of interest that we can continue analyzing this together and achieve more reliable estimates of human dose tolerance for radiation therapy. So there you go. What do you think?
All right. Thank you so much, Jim. If anyone else has any other questions that you'd like to answer in the chat, I think now would be the best time. If there was anything that you didn't get to, we can take just a couple minutes to do that. We don't want to run too late.
Someone asked what software I use. It's the DVH Evaluator is the software that I developed. Here at Hopkins, they have another one called
All right. Well, thank you so much, Jim. If there's no other questions that you want to answer, I think we can wrap it up.
So the journal papers are out there. I hope everyone has access to seminars in radiation oncology. The introductory article is free. QUANTEC, of course, is open access. TG 101, all the physicists can get to that. A lot of this data is accessible.
Okay. So the slides will be available on wepass.com. You can register to become a subscriber. And then we'll have them in the library for anyone who does want to subscribe. There are different levels of subscribing. And we hope that you all can join us for our next free webinar. Thank you so much for attending our free webinar series. If you'd like up-to-date information about upcoming webinars, be sure to follow us on Facebook, Twitter, or Google+. And if you have any future speakers that you would like to recommend, you can contact me directly via email, christina@wepass.com. And we also have a short survey after the webinar that we would really appreciate if you have a moment to take. It'll help improve our free webinar series.
Okay, wow, that's a good audience. Thanks a lot.
Thank you again, Jim, and thank you to everyone who attended the webinar tonight.
Yep, okay. Have a good night.
Good night, Jim.